Okay. Everything is good. It's a bit loud. Yeah, I'm opening. Okay. For some reason, I'm not allowed to change the volume. I don't know why, but I'm hearing a bit echo, but it's also fine. So these are not active. I cannot change them.
It was indeed. Can you speak now?
Is it better now? Maybe now it's
Maybe more.
better. I think it's better,
Yes.
No? Perfect. And you can hear me still, right? Perfect. Okay, let's get it started. Good afternoon. Welcome to lecture 11 of computer architecture. We were not ready to start. So today I'm going to continue what we have left off in memory controllers regarding the service quality and performance. We're going to discuss a lot of more techniques in the line of being more general and also the cost being low cost in these techniques. We're going to see different techniques, and tomorrow Professor Mutlu will be back and he will teach memory robustness, which I'm already excited about that lecture. So it's going to be a lot of fun. Okay, so remember about Maslow's hierarchy that we discussed regarding having safety and security is essentially the lack of quality of service can be categorized at that level, which shows the importance of providing safety, providing quality of service in our system. And recall that basically we discussed how to handle this problem, how to provide QoS-aware memory systems. We discussed having about smart resources, essentially make each resource aware of the interference. And essentially each resource is going to be intelligent enough to manage the interference and lower the interference. It can be memory controller, it can be interconnect, caches, storage controller, and so on and so forth. But at the same time, there are other way of handling it, which is we categorize as dumb resources that we don't necessarily make each resource intelligent, but we try to reduce the load by using some other techniques at a higher level. We discuss about techniques like source throttling, which we're going to also see today specifically. We're going to see today about QoS-aware data mapping and to memory controllers and QoS-aware thread scheduling to cores. So, and we also discussed that these techniques can be combined together. It does not need to be only each of them, which indeed actually combining them is going to lead to a better solution, which we will see also today in some techniques. So essentially, we try to categorize different techniques in these four categories: prioritization or request scheduling, data mapping to banks, channels, ranks, core and source throttling, as well as also application thread scheduling. And we were in the line of prioritization in the previous lecture. We discussed this work, STFM, which is one of the earliest work in this line. And later on, toward the end of the lecture, we get to PowerBS in order to ensure parallelism, which we actually discussed about the fact that, like in the core, in out-of-order cores, we have a lot of sophisticated techniques in order to capture parallelism from the application. For example, using memory-level parallelism, out-of-order execution. So memory controllers should be aware of that and should try to essentially, make the process, preserve that parallelism for the memory accesses, and that can actually lead to much better performance. So PowerBS actually was trying to do in that line, and we discuss about this technique. So any question? Now we're going to see about some other works in this line. The first work which I'm going to discuss today is Atlas Memory Scheduler. So these works that I'm going to cover now, actually, detail is going to be less compared to PowerBS and STFM that we saw last week. So we're going to mostly focus on high levels, key ideas, and some high level results. So in this work, essentially the focus is to maximize system performance. We try to come up with a scheduler which can to make sure that we can get much higher performance. Remember that getting high performance can be also in the line of the providing fairness, but sometimes you can also sacrifice a bit of fairness to get better performance. So the goal for this work was only focusing on performance, which we're going to also see how we can think about fairness as well. So the main idea is that we want to prioritize the thread that has attained the least risk service from the memory controllers. So remember that our key insight from also previous lecture, as I said, that when some application has much low memory accesses, much lower, then probably they are also much more compute bound. So they are essentially they are operating on the core more often. So if we try to prioritize those applications, meaning that we service their requests as soon as possible, then we can actually make the processor active and keep it running, which can lead to overall better performance. Whereas those applications that they have a lot of requests to the memory controller, they are essentially also the processor is already stalled, probably because of all these memory requests. So if we also delay service some of these requests for some amount of time, that may not also cause a lot of low performance and inefficiencies. So that's the main idea of this work, to focus on those applications, those threads that they basically has attained the least service from the memory controllers. So that's the ranking technique we have. So we rank threads based on the attained service in the past time intervals. So we have some intervals such that for each interval we try to measure and estimate. And then we enforce thread ranking in the memory scheduler during the current interval. So essentially we chop the time into several intervals. In some intervals, essentially we learn about how or we try to basically record how many accesses each thread has, and based on that we make a decision for the next interval, and we can keep doing that actually for different intervals and to change the ranking essentially. So it works in terms of for the performance for sure, because basically prioritizes light or memory non-intensive threads. They are more likely to keep their core busy. So that's the key insight that why this work is provide better performance. So we compare this work Atlas with prior work in terms of system throughput, and essentially Atlas, we show that Atlas consistently provides higher system throughput than all previous scheduling algorithms. And in this plot, you can also see that we vary the number of memory controllers. When you have only one memory controller, meaning that essentially in this specific system that you have 24 core, having only one memory controller, you're essentially starving the memory bandwidth. So it's not a cautious design, but it's good to see how would the result look like when we actually starve memory controller. So as we reduce the number of memory controllers, Atlas actually provides higher improvement compared to prior work. And this is basically expected because so when you have low memory controllers or essentially you have low memory bandwidths, it's more important how you prioritize and how you schedule, right? So having lower memory controllers cause techniques like Atlas to provide better performance improvement compared to the baseline. But as you increase the number of memory controllers, you can see that many of these schedulers, they are actually working almost the same. So in a balanced system, I would say that, for example, for 24 core system, we have, for example, 4 memory controllers. So here is actually much more, these bars in the middle, they are actually much more in reality. But in fact, the bars in the lower part is actually starving the system, and actually the bars after 4 is actually the scenarios that you have a lot more bandwidth, which you don't have usually in today's system. Question? Yeah, and also in the line of system throughput, like here also in this work, we in this plot, we fix the number of memory controllers to 4, and we compare Atlas with RBS, and then we change the number of cores. So 24 cores and 4 MC is actually essentially this one, but here we change the number of cores from 4 to 32, and essentially we observe that by increasing the number of cores, we are observing higher performance improvement, and that's again because the ratio of the number of cores and memory controllers. When you have much higher number of cores compared to the number of memory controllers, the problem of memory bandwidth is more important, more severe, and that's why scheduling actually makes much more impact here. Okay, so let's quickly also go over some upsides and downsides of this technique. So one of them as upsides that is good at improving overall throughput. Essentially, compute-intensive threads are prioritized, and it's quite low complexity. As well as also we can do coordination among controllers, which here actually it happens infrequently, but this is something, for example, that we didn't discuss in PowerBS, because so in PowerBS you change the ranking. Actually, you come up with the ranking per batch, for each batch, and then so you're going to change the ranking quite frequently, which means that you don't have any capacity to synergize the whole system for that ranking. So the ranking, the memory controller keeps changing, for example, in PowerBS, because for each batch, you're going to have a different ranking, right? So that does not let you essentially to coordinate the other components in the system based on that ranking. But here in techniques like Atlas, you use the interval to learn, and then in the second interval, you fix the ranking, right? So you have some time that the ranking is fixed, and for that time, actually, you can synergize other components based on that ranking, other memory controllers in the system, maybe also interconnection network, caches. So basically, you have possibility to synergize different components in the system based on the ranking that you have done in the previous interval. And I think that's also one of the good things about this work, which you can actually make much more global decisioning. But also as a downside, the lowest and medium rank threads get delayed significantly. So it can actually lead to high unfairness. Also, yeah, I think that's the main problem of this work, which in fact, in this work, we focus only on performance, but it can actually lead to quite bad fairness if we have threads that they have, they are frequently ranked as lowest and medium. But if you're interested, you can read the paper. It's going to be also one optional reading in our homework. Okay, any question? So the next work is thread cluster memory scheduling, TCM. So in this work, we first try to actually show this trade-off between the fairness and performance much more clear. First of all, so in the y-axis, we are reporting fairness. And for that, we are using the essentially metric, which is maximum slowdown. Remember that in previous lecture, we discussed about fairness metric, which was maximum slowdown divided by minimum slowdown, right? So that metric is necessarily not good because usually you don't care about the minimum slowdown, right? You mostly care about what is the maximum slowdown because that shows, which application or which thread actually is being affected much more. And also, if you use this maximum slowdown divided by minimum slowdown as a fairness metric, this can be also quite a bit misleading. Because one way also to do that is you can design a terrible actually scheduler, and you can say that you basically slow everything. You slow down these threads or many applications by great amount, like 5 times. But in the end, your fairness is 1. So your scheduler is fair depending on your metric, but clearly that's not a good scheduler, right? So by using such metric, like we want to minimize the maximum slowdown in the system, that actually can lead to probably better solutions. So that's why we are in this paper and also later papers in the line, we try to focus mostly on minimizing the maximum slowdown in the system. So that's one thing. And in the x-axis, we are reporting weighted speedup. And essentially, weighted speedup is a metric which when we have multi-applications. So here you're running different applications, or let's say different threads, which each thread belongs to the different application, right? So it's not a multi-threaded application. It still is a single-threaded application, but you have several threads. So when you run them together, each application has a slowdown. So in the end, so you have a different performance per thread or per application. The way you combine them, you can actually use metrics like weighted speedup, which you can also check the paper for more detail. But that's one of the way to report the performance when you have multiple applications. So ideally, we want to be here. Like we want to have a scheduler which provides the highest, let's say, weighted speedup, and also the maximum slowdown should be 1, right? So we want to be this down corner. But now we are actually showing, different techniques and how they, belong to this plot. So Atlas, which we focus mostly on system throughput, actually belongs here. So you can see that relatively provides good performance, but in terms of fairness, it's not very good. PowerBS actually, try to be much more fair. So the maximum slowdown is lower, but in terms of speed up, we don't provide good performance. STFM shows that, compared to these two works, is not very good. And that's how actually research has actually evolved. So in the beginning, STFM was very good because there were no other works in that line. But, as you do research more and you basically innovate more, you're going to get to better techniques. So, and FRF-CFS basically provides actually not good performance compared to these works, and also not good at fairness. FCFS for these specific applications, like 96 workloads that we tested, actually provides relatively good fairness, but in terms of performance is very bad. So this shows actually like the room for how we can improve. Essentially, we need techniques much more in this line, right? So we can see that we still have room for improvement. So no previous memory scheduling algorithm provides both the best fairness and system throughput. So, which is good. We can do research here. So let's compare throughput versus fairness, like how we need to tune our decision when we want to get better throughput or when we want to get better fairness. So throughput bias approach, essentially we need to prioritize less memory intensive threads. These threads, thread C, B, and A, you can see that as we go up, they are less memory intensive. So essentially in this throughput bias approach, we can try to prioritize the threads that they are less memory intensive more and more. So this is good for throughput. However, it can cause a starvation for thread C, which in the end can cause unfairness. Whereas for fairness bias approach, different threads, they take turns accessing memory. So it can be thread C, thread A, and thread B, and basically you rotate, this turn. So essentially here, these applications, they don't starve. However, thread A is not prioritized, which can reduce the overall throughput of the system. So as a result, so this is slide saying that single policy for all threads is insufficient. So we need to be a bit more complex here to provide better techniques. Professor Mutlu actually usually use this analogy, which is interesting. I can also mention here. He says mice for thread like thread A, and elephant for thread C and B. And essentially in techniques like this, when you try each mice and elephant, they gonna take turns, for example, to go out of their door. Elephant can actually, stomp on mice, and then we're gonna be in the issue. Whereas if mice, they can quickly go out. So in terms of performance, you can essentially let the mice go out very, very quickly. And then you need to deal with elephants, which are much harder to go out. However, if you have a lot of mice, then you might run into issue that elephants cannot go. So I just thought that this analogy might be also interesting for you to know. Okay, achieving the best of both worlds. We can have basically categorize mice, or let's say threads with low memory intensity as in the higher priority category. And for throughput, basically bias, we can prioritize memory non-intensive threads. And for fairness, we can actually have the separate group, or here we can call it cluster. That's why we call it cluster scheduling technique. So you can have a different cluster for these other threads which they are memory intensive, or let's say elephants. And for fairness, you can basically handle these separately. So unfairness caused by memory intensive being prioritized over each other. So there might be different elephants, different sizes. So essentially here you might get some unfairness by scheduling, keep scheduling, for example, the thread A over thread B. So in order to handle that, we try to shuffle thread ranking. So in the cluster, which used for memory intensive threads, we try to shuffle the thread ranking to to get to different thread ranking time to time. But we try to actually do it much more intelligently, in a way that memory intensive threads have different vulnerability to interference. So we try to shuffle asymmetrically. So it's not always shuffling, like rotating. So the shuffling technique is a bit more intelligent here. To make sure that we get to the better technique. Question? Yes. So we're going to see, but for example, MPKI, for example, is one of them. Like the number of miss per kilo instructions, like how many miss per kilo instruction each thread has, can be one metric, for example, right? And then, of course, you need to have a threshold for that. The problem, all these techniques actually are working based on some threshold in the end, to categorize. And that's actually a core problem of all these techniques, which I'm going to get to that also later. That we need to get to some techniques to get rid of all these thresholds, essentially.
Isn't latency also one of the factors, like particular application is expecting a higher latency?
Yeah. You can think of many different techniques. The problem is that we also want to be simple, right? So, like the number of metrics that you can check to categorize between memory intensive or memory non-intensive, you can think of different actually techniques, different parameters, but it's not like MPKI is easy. Is one of the easiest way to categorize, and a lot of works actually show that that's a good estimation. But I agree, there might be many other metrics that you can think of and also combine them. But as you go, you're gonna get to more sophisticated technique, and that may not also improve your estimation accuracy significantly. So yeah, so we should be careful. Good question. Okay, so in this work, we group threads into two clusters. Essentially, memory non-intensive, they're going to be a cluster by themselves, and memory intensive, they're going to be also intensive cluster. And then we always prioritize non-intensive cluster over intensive clusters. So then we have high throughput because the fact that we are scheduling or prioritizing non-intensive cluster, and but for fairness, which might happen actually in the intensive cluster, we try to shuffle the thread ranking. Okay. So yeah, here we try to essentially sort threads by MPKI, misses per kilo instruction. As we get to higher MPKI, basically the application is much more memory intensive. So assuming T is the total memory bandwidth usage, among all these threads, we essentially categorize the non-intensive cluster, alpha T, which, for example, alpha can be 10%. Like those threads that they don't consume more than 10% of the memory bandwidths, we cluster them as non-intensive threads. And other threads, they're going to be in the intensive threads. But you can see that now this alpha is another parameter. Yes?
Is this for considering asynchronous issue of memory read counts? Because in that case, there might be an application which is overlapping the memory read with the compute bound part very nicely. And so it's not necessary that an application with higher amount of DRAM memory reads is necessary if you have asynchronous.
Well, that's true, but you should have, I agree. I mean, there might be some application that you have. So the thing is that usually applications that they have too many, there might be some corner cases, I agree. But usually applications that they have too many requests at the memory. So first of all, they are accessing memory. It means that they are not heating the cache levels. So that's one thing we should understand here. So that when application heat a lot in the cache, that comes because of the locality, which shows that actually the application has good essentially data reuse, as well as the arithmetic intensity is quite high. Like the flops per byte is high because these metrics are related to each other. So you need to, when you are utilizing the core well, you are doing a lot of computation. As you say that you're hiding, so in order to be able to hide, because the computation latency is very much low most of the time. So in order to be able to hide, you hide with memory accesses. Those memory accesses should be also fast. If otherwise, very likely, you don't have enough computation, to hide the high memory access latency that you have. You know what I mean? If the application is generating too many memory accesses, then you're not hiding much also. We can argue, we can discuss more if you want, but yeah.
I was thinking that regardless if you hide it or not, you will be ending up generating the same amount of memory access.
Yes.
Independent of whether you pipeline the computation or
No.
not.
But the thing is that your computation, if you're, my point here is that when you have too many memory accesses, potentially the core is already stalled or will be stalled soon. So, and actually that stall time is also going to be quite long because the application has too many memory accesses. Whereas when the application generates very low amount of requests, then the core is actually doing a lot of computation already. So if we try to accelerate that, then we can keep the core active, which in the end going to help that. So it's very hard for me to imagine an application that has too many memory requests, off-chip memory access. It can be actually L1 cache access, which can, because of the locality, they are heating the L1. But if the application has too many off-chip memory accesses, back to back, it's very hard for me to believe that that application is utilizing the cores well, because the computation latency is much lower compared to the memory accesses. Do you agree?
In Macmil, oftentimes you try to fetch data for the next iteration in the current iteration. So for the next iteration, you are issuing the memory call right now.
Yes.
Overlapping with the computation that for the current
You're
iteration.
talking about prefetching.
Yes.
Prefetching can lead to some essentially, prefetching can lead to some corner cases. I agree. That's what we are not covering in these works and in these lectures. I have a slide through the end that what we have not covered. But yeah, if you have prefetcher, that you're in a different world, because prefetcher actually can go, forward and try to prefetch. So the memory access pattern that you're observing is not coming only from the fact that you're executing this, these instructions, which can lead to different scenario. I agree. Good. Okay. Oh, yes.
because it can make requests, right? So it can hit to L1 or
Yes.
So how distinguish before it?
So yeah, so for us, that's a very good question. So here, when we are saying that memory intensive, we are talking about off-chip memory intensive. Yeah, exactly. So if the application generates a lot of memory requests and those are hitting in L1, so far so good. We don't have problem with that, right? But we care about application that they need to use the bandwidths, off-chip bandwidths, and that's memory control is trying to utilize that memory bandwidth.
But before executing the thread, scheduler needs to schedule them, so they will.
No. That scheduler that you're talking about is the OS scheduler.
Oh, okay.
We are in a different scheduler here. So that, so yeah. And OS scheduler actually does that in, in much, it's not in that fine-grained manner. So usually it's around, I don't know, in millisecond, or sometimes if you are very lucky, it can be also in microsecond, but usually it's at millisecond. But here we are talking about nanosecond. So there are some threads that they are already scheduled by the OS, and now in the hardware, we need to schedule them. Good question. Yeah. Any other question? These are good, actually. These are really good questions. Okay, so the cluster threshold that we used was 10%, but you can think of, changing it, but at the same time, as I said, having all these thresholds make the confidence of this technique low. As long as, if you have a technique that can learn the threshold online, that can be good. Okay, you have you can think of some machine learning technique that you learn the threshold, and what would be the good threshold to use? That might be a good technique, but if you are using some workloads that you have already now, you run it, and then you tune the threshold based on that, then basically you have a lot of heuristic here, and your technique is not going to be optimized well for future applications. Okay. Yeah. So now we want to discuss about between clusters. So now when we have clusters, now we can prioritize non-intensive cluster over intensive cluster all the time. So the idea here is that these threads in non-intensive clusters, they are not gonna get more than 10% of the memory bandwidths. So they may not, or they wouldn't cause a starvation for threads in the intensity or intensive cluster. So that's a key insight here. So that increases system throughput and does not degrade fairness as well, as I discussed now. Okay. So, but how we can do, the scheduling in the non-intensive cluster, that's more interesting. So we can essentially prioritize thread according to the MPKI. So the highest, basically, we can rank the threads, and essentially least intensive threads has the greatest potential for making progress in the process, right? So we can actually have this, sorry, these are in the non-intensive cluster. I got confused. Yeah, okay, I'm sorry. So in non-intensive cluster that already prioritized over intensive cluster, also we might have different threads. So how you rank them, you can actually also rank them based on the MPKI. So essentially, again, we prioritize threads that they have the lowest MPKI over the other threads in that cluster, which in the end increase system throughput. But in the intensive cluster, we need to shuffle essentially the priority. So basically, we periodically shuffle the priority of threads. There is a thread here that we are now providing the highest priority for that. But in the in the next epoch, in that interval, we can keep, or in that epoch, we can essentially shuffle the prioritization to make it more fair. So now, so if you implement this technique by itself, actually that improves fairness for sure, because you are shuffling, and you are not starving. But the question is that, can we do better? So is treating all threads equally good enough? The problem is that equal terms basically would not, result in same slowdown. So that's the issue we have here. So we did some case study, and that kind of case study you have also observed in the past, like two intensive threads contending, like random access and streaming, which we have also discussed it in the previous lecture. So which is a slow down more easily. So you have observed these results from our previous studies that, essentially a streaming access usually, so essentially when you prioritize random accesses, the streaming, basically experience 7 times slowdown here. And when you prioritize the streaming access, the random access is slowed down more, like 10 to 12. So in this picture, we try to actually show the, why this is happening. So we have different banks. So in our previous example, we were discussing about like one bank, like single bank scenario, but here we have multiple banks and we have multiple rows. So when application has random accesses, you will be able to likely, use multi-banking. So those accesses can be mapped to different banks, which they can be serviced, from these banks. Even though, so the locality that you can get from one bank is not good. So you don't have, for example, you cannot benefit a lot from row buffer, for example. But the fact that you can distribute access across multiple banks, that's a good thing for you. And you need to activate different rows to get your result. So all requests in parallel and a high bank level parallel is when we have. However, in the streaming access, a lot of requests are actually going to the same bank. And all these requests are going to get to the same actually row because, it's a streaming access and you can benefit from, row buffer locality. So all these are going to be accessed the same bank row in one bank. So all requests goes to the same row and high row buffer locality. So in that sense, you actually have good performance because you have high buffer locality, right? But now when you have these two together, the problem, starts. So if it happens to, get to schedule the streaming accesses before the random access, then we're going to get to this problem that essentially this random access is going to be stuck here for a long time until we serve a lot of these streaming accesses. So essentially, now we discuss about this, kind of insight here that when you have an application with random access, it's actually much more vulnerable to interference. So that's the idea here. And then we define a metric named niceness to quantify this. So essentially, this metric niceness can be high and low. When we have bank level parallelism, which is the application is much more vulnerable to interference, and when we have row buffer locality, which this application is much more aggressive in a sense, this application can cause interference for us. Then we can actually combine these two metrics in order to get niceness. So essentially, bank level parallelism make the application much more nicey in the line of niceness. That's why it's plus. And the row buffer locality actually reduce the niceness of the application or thread. So we calculate the niceness, and based on that, we can actually shuffle. So TCM actually uses a quantum-based operation that essentially we chop the time in different quantums or different intervals you can also think of. But these are actually relatively long, like 1 million cycles. So in previous quantum and then current quantum. So during a quantum, we monitor thread behavior. So in terms of memory intensity, bank level parallelism, and row buffer locality. And at the beginning of the quantum, we perform clustering and compute niceness of the intensive threads based on our observation from the previous quantum. And then essentially we start doing scheduling and we do shuffling. But that shuffling is actually happening at much lower, intervals, like shorter intervals, which is around 1,000 cycles. So within that quantum, which is 1 million cycles, you do shuffle. And every time you do shuffle, you wait for 1,000 cycles around, and then you do another shuffling. And this shuffling is actually happening based on the niceness of the thread, essentially. Question? So it's such a technique that essentially you use your past to learn and then predict for a, you know, a near future, which then you can think of, okay, why would I be able to, you know, get good confidence in the next interval, in the next quantum, you know? There might be some applications that they change their phases quite frequently. So then your learning in the previous past may not be really reliable in the current time. So, which is correct, and that's one of the, you know, problems of all these techniques, you know, that you use some history to learn and then predict. So, but that can be also kind of the problem of learning in general. So it's very hard to do some decisioning or scheduling techniques for applications that they have fine-grained frequent phase changing, and that's actually very hard to do. Okay, question. Yes.
What if you have a large number of threads in the non-intensive cluster, and because of that a single cluster in the intensive thread remains hard for very long, which again we would not expect?
Yeah. So basically, you're saying that we put an thread in a non-intensive cluster, but that trend happens to be intensive in that quantum that we are looking at. No.
Since we, like, assuming a case where we have quite a large number of threads placed in the non-intensive cluster and very few number of threads in the intensive cluster, and since we are executing the non-intensive cluster, the threads in the intensive cluster will
can be starved. That may not happen because assuming the intensity of these application threads, you know, does not change. That may not happen because we use only 10%, like for that alpha that I discussed, we only categorize like 10% of the bandwidth usage as the memory non-intensive. So these threads are not supposed to actually starve the bandwidth. Sorry, yeah, exactly, to use the bandwidth a lot. So that's the thing. However, this can be the problem that, you know, in the next epoch or next quantum, these threads can be, you know, they can change their phase, you know, they can be different. So then a thread which is, you know, categorized as non-intensive can actually become intensive. And then you're going to be in trouble. That's correct. So one way would be, you know, playing with these quantum, how many cycles, you know, you make, because you need to, so when you're learning and when you're observing, so you need to make confidence, right? How much basically time you are waiting for making that confidence. So you can play with that. But if the application is very much, you know, and those applications that they are doing phase changing that frequently, they may not be that also a lot. But for that, I don't really have a good reason, a good solution for that. You know, potentially that's a kind of a corner cases for such techniques. You can also think of, okay, reducing basically this quantum time. Like so now we are making decision for 1 million cycles, which shows that if your decision is correct, then you are going to be in a happy phase. You know, for 1 million cycles, you don't need to do a lot of decisioning, and you're just making a scheduling based on the decision you have made. But this may not be effective if the application, you know, change phase a lot. So then probably we can also reduce these, you know, the quantum cycles to be much more, you know, sensitive to that changes. But that comes at, you know, cost. So, okay. Good question. Any other questions? Okay, so in summary, the scheduling algorithm, at first we have highest rank. We essentially request from the higher rank threads prioritize. So first, non-intensive cluster, always prioritize over intensive cluster. And then non-intensive cluster, we have the lower intensity, you know, the lower MPKI has the higher rank. And then in the intensive cluster, we shuffle the rank. And among these also, we have row heat. So row buffer heat requests are prioritized. So still we try to, you know, maximize the benefit from row buffer heat. And then also all this, all the requests are prioritized, meaning that At some point, if you have everything is equal, then your tie break is row heat. And then if in row heat also you don't see difference, maybe then your tie break is the oldest, essentially. So you have that level of scheduling in this technique. Make sense? Okay. So we showed in the paper that the overhead is actually relatively small, and we compare against prior work. Let's see how we land in this plot, which we showed before. So essentially TCM lands here, which provides much better performance and also, you know, relatively good fairness. So the TCM fairness is around PAR-BS. However, it provides much better performance. In fact, TCM provides better fairness than PAR-BS has. So TCM, a heterogeneous scheduling policy, provides best fairness and system throughput compared to prior work. Another interesting analysis in this paper is we try to change the configuration parameter in this technique and show the trade-off between fairness and throughput. So in FRF-CFS, for example, AMD has a technique that FRF-CFS cap. You can change the number of how many times you can essentially reorder a request over, you know, other requests in the queue in order to maximize the row buffer locality, essentially. So when you want to do this FRF-CFS first row, so in order to get benefit from the row buffer hit rate, you're gonna reorder requests, right, in the queue that you have. Like how many times you are reordering? There is a cap. In AMD, for example, they have a cap that you can actually control that. So if you change that number, that cap, this is going to be, for example, different results that you're going to get. So in terms of fairness and also in terms of performance. The thing is that it's very hard to reason about this, right? So by changing the parameter. STFM also has some parameters, and when you change those, you know, you don't get to a technique that by changing parameters, you can see different trade-off. However, in TCM, by changing the parameters like the alpha, for example, you can actually see a nice trend, which you can actually use it as a basically the way for example, operating system to manage TCM better, you know, depending on the fairness and how much fairness, how much throughput they are expecting from the memory controller, they can play with that parameters in TCM because it's easy to, you know, reason about, you know, how when you change that parameter, how much is getting to get a better performance, but you know how much you're lowering the fairness. So essentially, you can reason about this trade-off. Question? Okay. So yeah, in summary, cluster threshold is a tunable knob, and OS can trade off between fairness and throughput. Also, we can enforce thread weights. So essentially, OS can assign weights to threads. So OS may have some priorities. You know, the operating system may want to, you know, prioritize some threads over other threads for some reason that, you know, depends also on the programmer. So operating system can assign weights to threads, and TCM enforces thread weight within each cluster. This kind of thread weight can be also done with other scheduling techniques that we have discussed today and also last week. But that's one of the things which is kind of limiting in our today's systems. Like, as far as I know, the memory controller in today's system are not much aware of the priorities that we have at the operating system. And I believe that this can be actually something that someone can easily, you know, implement, because that kind of information from the operating system to the memory controller is quite vital, because that is very important to ensure the quality of service that we are expecting from the system. Okay, so as a conclusion, basically, this technique provides both high system throughput and fairness. And also, yeah, we have two clusters, non-intensive and intensive clusters. Non-intensive clusters for throughput oriented and intensive clusters for fairness oriented. And then we also shuffle basically threads based on niceness of them to provide better fairness. So as upside, it provides both high fairness and high performance. It caters to the needs for different types of threads, like latency versus bandwidth sensitive, and also relatively simple. However, basically scalability of this technique to large buffer sizes is questionable. And the robustness of clustering and shuffling algorithms, as we already also discussed, like because you learn from the previous quantum and then you're gonna use it. There might be application that they change phases and you cluster one thread as a non-intensive thread, but that thread happens to change the phase, then the robustness of the technique is actually not good. And the ranking is still too complex, which we're gonna also see in some future work, how we can reduce the complexity of the ranking. If you're interested, you can check the paper for more detail. And also these micro topics, which this paper was also selected as a topic. It's a shorter version of the paper. Question? Okay. Let's take, I think if there is no question, we can take break until 2, actually let's have 15-minute break. It's gonna be 2:22. So we'll be back at 2:22 and we continue. Okay. All good, thank you. So let's continue. The next technique is the line of blacklisting. The threads that they are problematic, so we try to blacklist them. This technique named Bliss, actually, coming from blacklisting, which actually is kind of quite simple technique. The focus was much more in the line of reducing the complexity of the schedule. So the problem we focused here was more or less in the line of how we can provide much more simpler memory scheduler, but at the same time also provide good performance and fairness. So the thing is that when we do ranking across, so essentially we do monitoring and across different threads, and then we do ranking. I mean, it can be any of the prior work, but essentially at some point you need to do some monitoring and then you rank threads. So enforcing, and then you need to enforce ranking based on some combinational circuit to schedule them for the execution. So the problem is that full ranking increases critical path latency and area significantly to improve performance and fairness. So in order to provide good performance and fairness, we have quite complex full ranking, circuitry, which that circuitry can be quite complex, can cause, high combinational latency, a lot of area. In order to reduce the latency of that, you can actually also make it more parallel and make it more sophisticated, but then it comes at a cost of area. So in the end, so that's one of the reasons that these techniques are not simple. So in this work, we try to discuss about this trade-off in triangle: performance, fairness, and also simplicity. We have observed performance and fairness trade-off in previous work, but here also we want to see the simplicity. And we are using a radar chart here, which is actually quite interesting chart when you have different metrics and you want to show a nice trade-off between them. You have different scale, and then you connect essentially the why the slides are playing on their own. Anyway, so you connect these, the end of these scales, meaning that in an ideal case, you want to have a technique which has the highest fairness, the highest performance, and also the highest simplicity, essentially. But then it says that basically techniques that they have the highest area in this, for example, rectangle. So here is a rectangle because we have 3 metrics. It can be square, it can be hexagon, for example, or any of these. So the techniques that they cover higher area, then they are potentially a better technique usually. But take it with a grain of salt, because in the end, not all these metrics are equally important. We have different, in different scenarios, we might want to prioritize fairness over performance or over simplicity. But FRF-CFS actually is like that, based on the analysis that we had in this paper. Like fairness is around this location, performance, and is actually also quite simple. So you can think of having a technique like FRF-CFS is actually kind of a simplest technique that we can come up with. Which FRF-CFS is actually unaware of the application. So we are not, FRF-CFS is not aware of the application, and we don't do ranking essentially. Other works, PowerBS, Atlas, and TCM, also you can, based on the numbers that they report in the paper, you can actually, categorize them here. You can see that, for example, PowerBS is actually quite fair, relatively good performance, but not very simple. Atlas is actually quite simple, but then the fairness is not good, performance is good, and TCM is something around that. So none of these works actually, they are, simple enough. So they're quite complex. So now the question is that, is it essential to give up simplicity to optimize for performance and or fairness? So our solution in this work is Bliss, which is actually, shows that how we can achieve all 3 goals. So how we can basically be, technique which is provide good fairness, good performance, and also at the same time quite simple. So the key observation here is that we don't need to do full ranking in many cases, it's sufficient to separate application into two groups rather than do full ranking. So we do monitoring and then we rank them. We don't rank them. We group them into different group, vulnerable and inference causing. Like some applications, like for example, with random memory accesses that we also discussed in the previous work, they are much more vulnerable to the interference. And some applications with streaming accesses, they are causing interference a lot. So you can group them nicely like this, and then you essentially try to prioritize vulnerable over interference causing application. So that's the first benefit, which low complexity compared to ranking. And the benefit, second benefit is that it lowers slowdowns than ranking, essentially. Okay, so how to classify applications into two groups? We have another observation that serving a large number of consecutive requests from an application could cause interference. So the basic idea here is that we group application with a large number of consecutive requests as an interference causing. So essentially, and then we try to blacklist them. And we deprioritize blacklisted applications. And then we clear blacklist periodically, like thousands of cycles. So by reducing this time, like the interval that we are clearing our blacklisting, this causes that, for example, for the application that they change their phase quite frequently, we don't cause problem for them. And also, we are much more sensitive, and you can actually change your decisioning quite frequently. So that's a basic idea of this technique, and this provides quite low complexity and finer grained grouping decision, which lead to lower unfairness. So the fact that you are making these decisions at every 1,000 cycles, this give you much more control on fairness. You are not causing a starvation for any of these applications. Whereas, for example, in TCM, in clustering approach, we discuss about like 1 million cycles, like, and that can be actually cause to unfairness if some applications they change their phases. Question? Okay. Yeah, so in this picture I already showed, like blacklisting, this work, Bliss, actually, comes at this trade-off, which is quite simple and provides very good fairness and also performance. So Bliss is the closest scheduler to ideal. Okay, and in this plot that we also have shown before, when we compare unfairness and performance. So here, lower is better. It's a bit different. And performance, not different actually. And higher performance, also higher is better. So essentially, remember that the ideal was this corner. So these are different techniques. But Bliss, which is this black circle, it shows that actually improves performance by 5% and reduce the unfairness by 21%. So blacklisting achieves the highest performance and also balanced performance and fairness compared to prior work. And is also quite simple. Okay. Any question? So we can be simple and effective in this case. And in terms of complexity, we report a scheduler area, and you can see that ideally we want to be here, which is quite simple. And also in the x-axis, we are showing critical path latency. So we want to be fast in our scheduling decision, and also we want to have quite low area overhead. So different techniques, actually, they land in different locations of this plot. FRF-CFS is one of the simplest technique. PAR-BS is actually quite complex. Atlas is somewhere here, like TCM is somewhere here. But blacklisting is actually, relatively simple. It's very similar to FRF-CFS. So the area is not that different, and the time that you need critical path latency of that also is around 2 nanoseconds, which makes it very good technique. Question? Okay. So if you want to learn more, here's the paper in ICCD that you can check. And here's also a longer version of Bliss in TPDS which you can also check it. Any question? I'm trying to switch the gear a little bit now. So far, we discussed about different single-threaded applications. So we discussed about, okay, having different applications running on the system, on a multi-core system, but each application has only one thread. Now, it's also very interesting to see that what should we do when we have one application with several threads? So you are actually running a multi-threaded application on a multi-core system. And this problem can be also even more interesting and challenging if you consider that you have several applications and each application is multi-threaded. So we want to learn, focus a little bit in that line to see how can we handle the issues in that for these applications. So if you want to learn more, here is a long lecture in this line of parallel application scheduling. But in these slides, I'm kind of providing some summary of that for us to know. And some part of it actually is going to be also covered in our future lectures in the processor-centric portion of the course when we talk about heterogeneity and how we can use a heterogeneous system to or asymmetric multi-core to accelerate bottleneck of the application, like the serial portion of the application. So you're going to see some of these actually in future lectures in this semester as well. So in multi-threaded, essentially threads in a multi-thread application can be interdependent, and as opposed to threads from different applications. So your decisioning across these threads actually can cause the overall performance of that application. So that makes it very different, how we handle it. So such threads can synchronize with each other through locks, barriers, pipeline stages, condition variables, semaphore. You guys are aware, I guess, of these parallel programming, right? So, and some threads can be on the critical path of the execution due to synchronization. Some threads are not. So it's important how we prioritize them, essentially. Even within a thread, some code segments may be on the critical path of the execution, some are not. So that's why we need to be careful about how we are scheduling in multi-threaded applications. So just to give you a bit more insight and also background, there might be some critical sections to enforce a mutually exclusive access to shared data. So here is an example of, for example, a code for a thread, which you have a normal computation, and then you have a lock to enter the critical section. So only one thread can be executing at a time. And when you have several threads, essentially each thread consumes some time on the compute part, which can be done kind of in parallel. But you can see that, for example, thread 1 is actually taking longer time, which might be because of not perfect load balancing, how much task you're allocating to each thread, or it can be also that, for example, this thread was expressing more cache misses, for example, or some other scheduling techniques that we have. But essentially, for any reason that might be here, thread 1 is taking longer time. But then, so that's why thread 2 actually reaches to the critical section faster and then get the lock and enter the critical section. So, and now thread 1, when it reaches to the critical section, should be stalled. And that's why, so now we are actually observing serial execution. So that's a kind of a serial bottleneck that we might have. Remember, how many are you remember about Amdahl's law? Parallel portion and serial portion, right? So Amdahl says that essentially the speed up that you can get from parallel programming or parallel execution is bounded by the serial portion of the application. But usually, but the thing is that serial portion is also not that easy to understand, because there might be some serialization which is happening through the parallel portion. And the critical section is one of them, right? Even though this can be categorized as the parallel portion of the application because you are basically launching several threads, but in that thread you have some serial execution some happening, we might get to some serial execution because of the critical sections. So, and that can limit the performance. So we need to extend the AMDA law, which we're gonna also see in later lectures, how we extend the, thinking of the AMDA law by considering all these different serialization effects in parallel application. So, yeah, and that here it caused basically, the serialization. And you can think of here that if when we are in this scenario, maybe, the thread which is in the critical section now, if we try to somehow accelerate it by prioritizing thread 2, then thread 2 is going to be done by the critical section faster, which makes the fact that thread 1 is going to also have lower idle time. So that's where actually scheduling and prioritization actually comes to play here. Good, makes sense. Another could be barriers as a synchronization points. So you have for each thread, they do some computation, and then you have a barrier to make sure that all threads synchronize, and then they continue. So now the problem is that different threads can reach to the barrier actually in a different point of time. So thread 1, for example, reach to the, finishes the computation faster, but then it needs to be stalled to get to the barrier. And then thread 2 is still lagging, like running, and then we get to the barrier. So again, you can also think of, okay, if I try to schedule thread 2 here, exactly, schedule thread 2, meaning that try to prioritize thread 2 in some of the memory accesses, then thread 2 is going to also reach to the barrier point faster, which in the end would cause better performance for the whole application. Another example could be stages of pipeline programs. So in some application, we have this stage programming that you have in loop, you have different code segments. And essentially each segment will be assigned to a different thread, like thread A, B, and C here when we have 3 stages. So now the thing is that you do some, basically, we have a queue, before each of these, units. And they get basically input, they give input to the stage A. So stage A needs to do computation and then generate input for the stage B. So in B, we are dependent on, for example, the input from the previous A, and then we can continue like that. So now they can see that here thread 1, which we allocate for scheduling, for running the segment A. So it executes and then stalled from the fact that it didn't get input from the previous iteration. And again, also, and then essentially it, B actually, so B is quite slow here. So the problem is actually, I guess, is the problem of B. So B is quite slow, which makes the C also, stall for a long time. And then the fact that C is stalled for a long time, it generates input for the A, actually, for the next iteration, basically cause it to be stalled. So some threads, they are actually stalling. So now here we can see that different reasons of that. So here, no, I'm sorry. I actually explained a bit wrongly. So so A, in order to put output in this queue should be empty. And the fact that B is slow, so this actually is not empty, such that A can put, putting data into this queue. So that's why we are stalling thread A here until B executes a little bit. And here also, now C is actually also stalled because B does not generate enough output, enough input for the C. So B is generating output, putting into this queue, and C is actually consuming from that queue. And since B is actually quite slow, now thread C or thread C cannot, or core 3 cannot be scheduled all the time because we run out of data to process on. So essentially, we can see that thread B is causing the problem for thread A and C, and that's why actually if we try to prioritize thread B or prioritize in different memory system level, this can potentially provide better performance for the whole system, for the whole application. Question? It was a bit complex to explain, but I think I made it. Yes. Yeah, it can be also in the loop. Yeah. Okay, so this is the paper. This is a paper that we discussed about this, the problem. So threads in a multi-threaded applications are interdependent, and some threads can be on the critical path of the execution due to synchronization, and some threads are not. And how do we schedule requests of interdependent threads to maximize multi-threaded application performance? So the idea is that we try to estimate limited threads. So in this example, I try to give you some insight, what would be the limited thread. So at the runtime, we should try to estimate limited threads, which is likely to be on the critical path, and then we try to prioritize the requests. And we essentially shuffle priorities of non-limited threads to reduce memory interference among them. So it's kind of a hardware-software cooperative technique to estimate limited thread. And this technique actually is based on all these three reasons that we already discussed, like which thread is contending more on the critical section, which thread is the slowest in the pipeline stage, and also threads that is falling behind the most in reaching a barrier. So we discuss all these three kind of actual reorder. So it should be, the last one should be the second one if you want to keep the the ordering of the slide. But yeah, so that's the overall idea of this technique. Here is also an example that you can also think of having this combined together. So we have 4 threads here. And so this black line is non-critical section. And then we have critical section 1, which is green. And then we have this waiting for synchronization or lock, which is kind of dashed blue line. And critical section 2, which is the orange rectangle. And also we have barrier. And critical path also can be shown with red basically line. So here, here's a critical path of the execution of these 4 threads in parallel. So with such a technique, which we try to estimate, so essentially in some time we do and we execute and observe, try to understand which is the limited thread. So we are in the phase of limited thread identification. So far we can see that most contended critical section is critical section 1. As we have been in that for a long time, in all threads. So essentially all threads are contending for that critical section. And then limited thread actually is changing. So now thread D is in the critical section of the, the most contended critical section. So thread D is in that critical section. So we basically prioritize that. And then thread B get to that critical section, we prioritize that, and then thread C we prioritize, and then thread A we prioritize. And then you can see that we essentially we save some cycles for this application. Okay? Good. So it improves the performance of multi-threaded application and provides a mechanism for estimating limited threads, and opens a path for a slowdown estimation for multi-threaded applications. However, this work, as any work, has some downsides. What if there are multiple multi-threaded applications running together? This can be actually much more exciting to look at. I mean, there are works on that, but you can also think of potentially we can combine these different scheduling techniques that we have discussed, right? So in the previous scheduling techniques, we discussed about having single threaded application. Now you can have also multiple multi-threaded applications, right? So you can potentially have some scheduling techniques within that application using such techniques similar to what I said, And also you can use some other scheduling techniques across all these applications. But whether or not, I mean, that might also not be ideal enough or optimized enough. So that's why this by itself can be also a very interesting research problem. Limiter thread estimation can be complex. We're gonna see a lot actually in that line later when we get to that bottleneck acceleration. So we need to identify the bottlenecks and then try to accelerate that. And that acceleration does not need to be only by scheduling. I mean, here is scheduling like scheduling the memory system level. It can be also, for example, using big cores. Like think about asymmetric multi-core, that your multi-core system consists of small cores as well as big cores. And if you identify bottlenecks, you can potentially schedule the bottlenecks on big core. Big core meaning that, for example, they are big out of order core, which they can actually provide very good performance for serial portion, essentially, right? And there are many small cores which they are not, each are not very good, but they can together they can actually provide very good performance for parallel portion. So if you can identify bottlenecks, you can potentially map them the bottlenecks to big cores and to accelerate, and that can accelerate the serial portion of the application, which in the end would cause better performance for the whole application. So we're going to see a lot in that line in our lecture in bottleneck acceleration. This work from João is actually one of the work that we're going to also discuss, how to identify bottlenecks and scheduling. So if you're impatient, you can actually check this paper, how we can do that. But here's a paper of PAMS, Parallel Application Memory Scheduling, which we already discussed it. If you're interested, you can check. And also the lecture about it. In the line of bottleneck identification and scheduling, this is like another work from, the work that I already, briefly discussed it. You can also extend it to utility-based acceleration of multi-threaded applications. So we're going to actually discuss all these papers later in the course. I think maybe in the next 4 or 5 lectures. Question? Okay. So remember that also we discussed about systems that they are getting more heterogeneous, and the designing the memory controller is actually becoming much more challenging. So this is a picture which I showed you before also. The current SoC architectures, we have very high heterogeneity. We have different CPUs. So here we can have large CPUs, small CPUs, GPU can be also hardware accelerators, DMA. You can also think of PIM. There might be some PIM engines here also. So scheduling them together is actually not easy. So I'm gonna basically, unfortunately, I don't have time to go into detail of these works. Some works that we have done this line, I'm gonna only flash the papers. Just to let you know, if you're interested, you can check later more detail. So yeah, heterogeneity is everywhere. Like this one is for Apple M1, and we have done basically we have lectures on that line also from previous editions of this course. And here is also kind of foreseeing our lecture in asymmetric multi-core, which I already also kind of foreseeing for you. Like in symmetric, you can have a SoC with all cores are similar. But today is actually SoCs are quite asymmetric. So you have large cores, small cores, and then it's very important what to map to the large core essentially. Okay, so this work, which I'm not gonna go into, which I'm not gonna explain it actually, stage memory scheduling is one of the work that we have done in this line of heterogeneity, more specifically here on CPU, GPU integrated systems. So in GPU, actually, usually, if you think, for sure you have worked with it. Usually, they are considered as a kind of a discrete system. So you have a GPU, which you connected on your motherboard on a PCI slot, for example, and that's a discrete GPU. And then also you have the CPU and main memory. So this kind of a discrete system, and essentially GPU and CPU, they are not sharing memory controller much. I mean, the memory control of the CPU is actually completely separate, and the whole scheduling of the GPU is happening through the OS call, and that's why actually by moving the data from CPU memory to GPU memory and start invoking the execution is quite time-consuming. So in order to reduce the time and also enable more applications in the line of applications that they can collaboratively benefit from CPU and GPU in a fine-grained manner, different vendors, they basically put CPU and GPU on the same chip, and they call it integrated CPU-GPU chip. For example, AMD have this APU, I guess, accelerated processing unit, which has a CPU and GPU. NVIDIA has it also. Intel also has, like in many of new Intel chips, you have graphic processor also on this CPU die, which can be used. So now that you have CPU and GPU on the same die, they may share also some cache level hierarchy or not. So in some cases, for example, they don't share L1 and L2, but in last level cache, they may share it. There are also some editions that they don't share any of cache levels, because it's very difficult to handle, the cache hierarchy when you have CPU and GPU on the same chip. But certainly they are sharing memory controllers, because in the end they're going to access the memory, and they are sharing the same memory controller to access. Now the problem is that the nature of accesses from the GPU and CPU are very different. CPU accesses are much less frequent, because your parallelism is limited. And also usually CPU applications are kind of latency sensitive. So you're very much important how to, you try to address the CPU requests faster to keep the core, running. Whereas in GPU, GPU actually generates a lot of requests. Like think about when we run one thread, which in the terminology they can call it, for example, NVIDIA, they call it, for example, warp. So that warp actually consists of 32 threads. So when one warp actually gets to the load request, that load request will generate 32 memory requests. Well, if the application is regular, those 32 memory requests can be coalesced actually to one memory request, but for some application, it can actually lead to 32 requests, And you might have thousands of warps, and all these are gonna get to the basically memory. And also note that in GPUs, actually, the hit rate of the caches is actually also quite low. Like the L1 cache hit rate is usually around 50, 60%. LLC hit rate is also quite low. So many requests actually, when they generate memory requests, are gonna also end up getting to the off-chip memory. So from the GPU side, we have many requests, and also these requests are not that latency sensitive. In GPU, you are capable of tolerating latencies to some certain point. So you are able now to increase some latency, cause some longer latency for GPU requests without sacrificing the performance of the GPU application, because GPUs natively can tolerate some amount of memory latencies by quickly scheduling or quickly switching across threads, different threads. So now the nature of these requests are different from CPU and GPU, and that's how you manage that at the memory controller is very complicated, And this paper actually showed that if we are not careful and we are using, for example, simpler scheduling techniques or some scheduling techniques that we have had in the past, they are not effective, or they may end up being too complex. So this paper, SMS, focus on how we can come up with a scheduling technique in that area. I just try to motivate you why this paper is very important, but I'm not going to explain how this paper did it. So if you want to learn about it, I very much encourage you to check this paper. Yeah, is it interesting or not? Can be. Okay, depending on the goals, essentially. And in that line also, we have done more works. Dash is another one in that line. And also in handling CPU and IO interference, which I also discussed it in the past as well. But all these works that we have discussed now, they provide, performance and fairness. We try to show a trade-off between high performance and fairness, but they don't provide, like if you want to have strong memory service guarantee, these works that I already discussed may not be effective enough. So sometimes you really want to, provide much higher guarantee. And so through the next slides, I'm going to discuss some works that, essentially they try to be much more careful and provide much stronger memory service guarantee. So there are lectures from the past. If you want to learn more, you can check. This work is one of them, like providing fairness via source throttling. Remember different techniques that we have discussed. This can be categorized as a dump resources that we try to provide fairness by throttling. I'm going to discuss some of these works, but first I'm going to flash some of them. This work also is again in the line of predictable performance, how we we come up with a model to use that for our performance and slowdown estimation. And Dash, which I already also shown, and other works. But in this line, now I want to focus a little bit, not much, but in the second, category, which much more in the dump, resources, try to, solve the problem, at the basically source level. So there are also lectures from the past in these lines for you. If you want interested, you can check it. Yeah. But one way is actually to do with memory channel partitioning. So essentially, you can partition your memory channels between these different applications. So here is an example. You have two applications, red application and blue application, red and blue, and they are generating requests that, for example, red application is actually accessing, going through both channels and accessing the memory, and blue application also the same, like use the both channel. And now you are seeing that we are observing some interference between red application and blue application. So one way to handle that is to do channel partitioning. So send all the requests from the red application to channel 0 and blue application to channel 1. So this can immediately actually solve the interference problem. I don't know why these slides have some animation that they go on their own. I usually don't like it. I know Professor Mutlu also doesn't like it. But maybe some PhD students that they were preparing these slides, they had that kind of animations. Okay. So memory channel partitioning, the goal is to eliminate harmful interference between applications. The basic idea is that to map the data of badly interfering applications to different channels. So we are using two key principles: separate low and high memory intensity applications, and also separate low and high row buffer locality applications. And you can also think of why this is a good, it's good to use these two principles. But I'm going to also show with some, some examples. So by separating by memory intensity, here you can see that these, again, these two applications, red and blue. So they're generating, red application is generating a lot more requests. And so when blue application generates some, requests, then is actually quite bad luck. So now this blue application probably needs to wait a lot for the red application to be done. So by doing that channel partitioning, you can actually map, handle all the requests for the red application to channel 0 and blue application channel 1. That would save cycles a lot for the blue application. But in this example, you can also see that this even saves cycle for the red application as well. So map data of low and high memory intensity application to different channels would be very useful. Another insight is, how different applications interfere at the row buffer. So you have two applications here that they're accessing different rows. You have, again, blue application and red application. Blue application, you can see that it's accessing different rows. meaning that blue application does not benefit from row buffer locality much, but the red application is actually accessing the same row 0. So in this timeline, you can see that basically red application has much lower latency in accessing the because it hits in the row buffer, but in blue application has longer latency. So this is a conventional page mapping, but if you do some channel partitioning, you can actually nicely handle requests for the red application in one channel, and then the blue application in another channel. So the idea here is that if we keep scheduling the blue application on the same bank, like using conventional page mapping, then the problem is that by having access to row 2, for example, you pre-charge the row and you activate another row. So now row 0 is not open anymore. And as we get requests from the row 0, actually we don't. Then we're gonna basically experience more row conflict, which is not good to happen. So that's why we try to, in order to reduce that interference, we try to have application with row buffer hit rate, relatively high row buffer hit rate in one channel. What's happening? Yeah, and another application with relatively low row buffer hit rate, or let's say quite random memory accesses to another channel. Okay, so here is a mechanism. So essentially, we profile up. Yes.
This does not seem account for background text, because like it is partitioning multiple things back, and then if the application is waiting for one time, there is another source which by hand also can become one thing. So if you are partitioning data, why not partition it in a more clever fashion to different banks, so that you don't serialize that part of the computation?
But here we don't necessarily talk about multi-threaded application. It can be actually different application, and each can be single-threaded. So that's the thing. So we kind of discussed about how we can provide fairness and performance for different single-threaded applications and also one multi-threaded applications. But now we are discussing about other works that they try to provide much stronger performance quality. So and that's why we are talking about channel partitioning, because channel partition, if you think about it, does not sound very good. In fact, in this work, actually, we try to do it nicely, and I will describe more. But overall, when you partition, you are in the risk of bad partitioning, because you may end up having a channel which is not utilized enough, and other application which you they might have a channel which is overutilized. So whenever you do this channel partitioning or any partitioning technique to make some isolations, you're in that risk. So that's why we are now focusing on that line, because it's very interesting how people can handle those cases. Yeah. Okay. So we profile applications, and then we classify application into groups. And then we partition channels between application groups, and we assign a preferred channel to each application, and then we allocate application pages to preferred channel. So that's why, so the profiling is happening at the hardware level, but the rest is actually happening at the system software, classifying and partitioning and assigning and memory mapping. And this technique is, again, also interval-based operation. So in the current interval, we profile applications in the hardware, and then we do the classification, partitioning, and assigning. And then for the next interval, we just enforce channel preferences. So these intervals also should be long enough because moving from one channel to another channel is going to be very expensive, right? So you cannot make these intervals short, and then you keep changing the channels. Okay. So our observation is that applications with very low memory intensity rarely access memory. So dedicating channels to them results in precious memory bandwidth space. So that's one thing which I already also talked about it, right? So you have channel partitioning, but if that channel is allocated to application which is low memory intensive, then that channel is going to be underutilized heavily. So, and also these applications, they have the most potential to keep their cores busy. So we would really like to prioritize them. And also they interfere minimally with other applications. So now we can actually also improve this work and come up with this integrated memory partitioning and scheduling techniques. So now we can actually benefit from both approaches, dump resources and smart resources. Was that smart? Yeah. And so we can basically we can always prioritize very low memory intensity applications in the memory scheduling. And also we use memory channel partitioning to mitigate the interference between other applications, which they are memory intensive. So we apply memory partitioning only, or channel partitioning for those applications that they are memory intensive, and those applications that they are memory non-intensive. They are basically, we are handling them just by prioritization at the memory controller, and they don't have this channel partitioning. So the hardware cost for a memory channel partitioning is relatively small, and for this integrated memory scheduling policy and partitioning and scheduling is also not that bad. So here are the results. Average over 240 workloads. And so we can see that essentially MCP provides, around 7% performance compared to the baseline FRF-CFS. However, combining with scheduling, IMPS can actually cause much better performance, like around 11%. Channel partitioning does not provide much performance compared to TCM, but by combination of with scheduling, you can get much better performance. But also, it's not only about performance. So you should also note here that when we use channel partitioning, we really want to ensure performance guarantee much more. So we are much more focused here on providing fairness, but not only fairness, actually quality of service. We really want to enforce that quality of service. So usually partitioning technique can come with some overhead. And we always need to be sure that we don't end up having that bad partitioning. And this is a beautiful picture that Professor Mutlu got in Zurich airport, which you can see that there are many channels everywhere that they are kind of empty. And then there is also only this channel, which is heavily utilized. You have a long queue. So there might be better channel partitioning in Zurich airport as well. Okay, so combining multiple interference control techniques, we have seen one of them. But then the key challenge here is that deciding what techniques to apply when, and partitioning work appropriately between software and hardware is not easy, but these are challenges. So here in memory channel partitioning and also adding this scheduling for the interference aware, that was relatively easy, the way that we discussed it. But that's not easy all the time, how you can combine approaches of in the line of smart resources and dump resources. So these two work, MCP and IMPS, together, they basically provide, it keeps the memory scheduling hardware simple, and it combines multiple interference reduction techniques and can provide performance isolation across applications mapped to different channels. As a general idea of partitioning can be extended to smaller granularities in the memory hierarchy, like it can be banks, subarrays, etc. It does not need to be only memory channel partitioning. You can also use this idea to do bank partitioning, subarray partitioning, etc. But as a downside, reacting is difficult if workload changes behavior after profiling, because specifically here with channel partitioning, moving from one partition to another partition, from one channel to another channel, is very expensive because you need to move a lot of data from one memory to another memory. If you do it in a more fine-grained manner, like at the subarray level, it might be easier, to change. Specific also benefiting from techniques like, like in-memory copy that we already discussed, like row clone, Lisa. So with that, you potentially are able to reduce load, reduce the overhead of that. But in general, reacting is not easy when you do partitioning techniques. And overhead of moving pages between channels restricts the benefit, which I already also discussed. So here's the paper. If you're interested, you can check for more detail. And you can also do source throttling. Which I think we can actually take another break, and then I will continue. So let's be back at 25, 3:25, 13-minute break. All good? Okay. So let's continue, I guess. Let's keep it. Okay, so let's continue these techniques in the line of providing strong performance guarantee. The next technique can be, using source throttling, which we kind of also discussed it in the last lecture, but here is a technique that we can use. So source throttling in general actually is a substrate that you can provide furnace with it. So there has a general key idea is that to manage inter-thread interference at the cores, meaning at the sources, and not at the shared resources. So in such techniques, we try to dynamically estimate unfairness in the memory system, and then we give feedback this information into the controller. And then that controller decides how to throttle. So throttle cores memory access rate accordingly. Essentially, we may throttle, or for some cores we throttle them, throttle down, some cores we throttle up. So whom to throttle and by how much depends on performance target, throughput, fairness, per thread, quality of service, etc. So one example would be if unfairness is greater than system software specified targets, then we can throttle down core causing unfairness and throttle up core that was unfairly treated. So the core that was unfairly treated, we will throttle up it, and meaning that core is going to get faster accesses essentially. So here is a paper that we're going to also discuss it now with some, at a high level, fairness via source throttling. So there are two components in this kind of works in FST: runtime unfairness evaluation, which is in hardware, such that we dynamically estimate the unfairness application slowdowns in the memory system and estimates which application is slowing down which other. And then we also need to do dynamic request throttling, which can be hardware or software. So it can be, so like hardware can decide, can basically enable or enforce that throttling, can decide and do that. It can be also at the software, like the operating system is observing different applications, and OS can actually cause, can throttle some applications. This throttling technique actually has been done in different layers of the computing as well, as you can imagine. So essentially in that component, we need to adjust how aggressively each core makes requests to the shared resources. We throttle down request rate of cores causing unfairness. For example, we can limit the miss buffers, or we can limit the injection rate, how quickly you put requests into the network. Okay, so this technique, again, also has different intervals. So in some interval, we do a slowdown estimation, which is a kind of runtime unfairness evaluation, estimating the system unfairness, find application with the highest slowdown, and find application causing the most interference find application causing the most interference for that application with the highest slowdown. And then we input, all these data to the dynamic request throttling. And if the unfairness estimate is greater than the target, we throttle down application which caused the interference, and we throttle up application which is caused to be slowed down a lot. So how aggressively each core, how we can adjust, how can we adjust the aggressiveness of the different cores? We have different mechanisms here. So one way would be to reduce the MSHR quota. Like we have this miss status holding register MSHR in processor, which with that you can actually keep how many outstanding memory misses you can keep, right? So if you so we can control the number of concurrent requests accessing shared resources from each application. If we reduce the number of quota in MSHR, that means that that application cannot have that many outstanding memory requests, which potentially cause that application to be stalled, and then reduce the rate to the memory system. Another mechanism would be also adjusting the request injection frequency. Like we control how often memory requests are issued to the last level cache from the MSHRs. So we have MSHR, which has its quota. You can manage that. And then within that quota, like how often memory requests are issued to the last level cache can be every cycle, can be every 10th cycle, for example. Then that can also reduce the load. You can adjust the load based on that. So we define different throttling levels for this work. Basically, throttling level can be from 100% to like 2%, and also so for each of these throttling level, we have different MSHR quota and also request injection rate. So when we want to have a throttling level 100%, meaning that throttle up, I mean, it's a bit confusing. We are not throttling 100% here. We are, which means that we don't want to throttle at all. So when we are in this scenario, MSHR quota is 128, which is the maximum, and then we request injection rate is every cycle. But when we want to throttle it, half, we reduce the MSHR quota to 64, and then we do injection rate every other cycle. And you can see different, numbers in this table, which we use to manage to adjust the aggressiveness of the application. Yeah, makes sense? But this needs also system support. Basically, different fairness objective can be configured by system support, by system software. Keep maximum slowdown in check. Basically, we want to have estimated max slowdown, less than target max slowdown for the fairness technique. And we want to keep a slowdown of particular application in check to achieve a particular performance target. Remember about this quality of service. There might be some application that you specifically want to have their slowdown less than something, less than some amount. So we need to do this estimation, and that should be less than target slowdown. So essentially, we need support from thread priorities. So this work provides support for thread priorities, which the system. Yeah, these are the different support that this work provides for the system software. When the OS wants to make these decisionings, like how to prioritize one application across other applications, or how to make sure that we don't slow down one application more than something, so that operating system has some target. And this technique actually provides that infrastructure that can be used, framework that can be used from the operating system. Okay, so source throttling alone provides better performance than a combination of a smart memory scheduling and fair caching in this work. Decisions made at the memory scheduler and the cache sometimes contradict each other. So that's why, so when you want to have a smart memory components, it's very hard also to synergize them. You might have a smart network, you might have a smart cache management, you might also have a smart memory controller. But it's also very important how to coordinate, across these smart resources. And that's very much by itself is also very interesting research direction, how we coordinate nicely different controllers that we have in our system. But the thing is that by source throttling, that kind of frees you from that coordination, that you might need to do. Remember, I discussed about CPU and GPU, for example, interference. There are some works, for example, from our group as well, that, for example, we just reduce the load for GPU. Like we know that GPU is generating a lot of requests. Time to time, we just throttle GPU, and that can fix the scheduling of GPU and CPU requests. Of course, that can come at price of some performance overhead, but as long as we have performance in check, maximum slowdown in check, and we are achieving the targets, there should be no problem. But neither source throttling alone nor smart resources alone provide the best performance. So it's very important we have kind of combined approaches to get to much more powerful techniques. Okay, so source throttling has some advantages, like core and request throttling is easy to implement, no need to change the memory scheduling algorithm, and can be a general way of handling shared resource contention, and can reduce overall load and contention in the memory system. So basically, it has its impact on many parts of the systems, not only on memory controller, for example. By doing this throttling, you are handling cache contention, potentially you are handling interconnect contention, memory controller contention, and so on and so forth. But it also has this advantage, like it requires a slowdown estimations, which can be very also difficult to estimate. And the thresholds can become difficult to optimize. Like a lot of these works are threshold based. This work and also prior works that I discussed. And that's actually kind of a hairy thing, in these techniques, like how much you can make confidence by having all these thresholds, how to effectively tune all these thresholds. And once you have different controllers, how to define these thresholds which can synergize together. So it's very hard. And that's why actually we need to move into techniques that they are, less dependent on the threshold, and such that you can actually, handle these problems more effectively and also more generally. Okay, so yeah, exactly. So by threshold, it's very difficult to find an overall good configuration. So there are many applications, and there are many applications also that you're not testing in them. So it's very hard to optimize that. But if you're interested, you can check this paper. It's actually also won the best paper award at ASPLOS 2010. And there are also other works in this line. HAT is another one which we have done for heterogeneous adaptive throttling for on-chip networks. And some other works in the line of on-chip networks, interconnects, which we might get to them also briefly when we discuss interconnects through the end of the this course. But yeah, there are a lot more in this line, which you can check if you're interested. Any question? Since we are still early in time, I would also like to also quickly go over this to broaden our thinking, because so far we have discussed a lot on memory controller throttling, not throttling, like scheduling at the memory controller level. I also showed some papers from the cache and as well as network, but there are many other components in the system, and interference can happen everywhere. This work, we focus on SSD, that they have, SSD controller, to how can we high performance and have fair scheduling across different requests at the SSD controller. So I will go over this paper at a very, very high level, because there are some, discussion in this paper that cannot be easily discussed in today's lecture for the interest of time. And we're going to have lecture also in Flash and SSD later. But I wanted to discuss this work today, to broaden our thinking. So Flynn, it's a paper that's published in ISCO 2018. And so the high-level idea is that different applications, or let's say different, like the problem, the high-level problem that we are focusing here is that previously SSDs actually have this SATA protocol, which still are also SSDs. Some of them they use SATA, which is a kind of the interface protocol that we have been using for hard disk drive. I think you know SATA. Connection. And SSDs, when they also come to play, they have that SATA protocol. And in SATA, essentially different process or different applications that we are running in the system, each they have a IO request queue, which kept in the memory, in our main memory. And then there is a OS level IO scheduling, which try to schedule across these queues and then dispatch. And then we have this hardware dispatch queue that basically OS makes the decision based on what to schedule, and then we send this to the SSD device to to get response. So that's the SATA based protocol. However, people show that basically it doesn't provide good performance or throughput, even though SSD theoretically can actually provide very good throughput compared to HDDs. And that's why people came up with a high-performance host interface protocol named NVMe. And with that, actually, we essentially, we remove that kind of OS block, that OS IO block in between, so that interference of the OS is actually gone. And each process we're going to be, connected. We're going to have a queue in the SSD device, kind of. And each process will, communicate to the SSD directly at the user level. So, and that provides very good performance by itself because you don't need to go into the OS, IO block system, but it's not, in terms of fairness and quality of service, it's not fair. It's not safe to do such things, because now there is no scheduling technique. And that was our observation, that was our insight, or let's say hypothesis, when we started thinking about this line of project and saying, now you have a different process. They can communicate with the SSD device separately, and there is no control. In the past, we had this OS that was scheduling across them, but now we don't. That's one thing. Also, when you do this scheduling at the OS level, you don't have enough information about what's going on at the storage, because there are a lot of information in the SSD which is hidden from the operating system. So operating system is not aware of that. And by doing actually scheduling at the OS level, we're going to get to suboptimal solutions also. So the thing is that NVMe actually gives us a very nice opportunity here that we need to do something because there is no scheduling. So we need to schedule nicely for high performance and fairness. But at the same time, if we do that, probably we're going to end up having a better scheduling, because inside the SSD device, you are aware of the characteristics of the application, the SSD that you have, and then you can potentially make better decisions. So yeah, so that's a problem. We actually tested on real SSDs with some applications. And we observed that when we, for example, run two different applications like TPCC and TPCE, these applications are observing different slowdown. And that was actually expected because there is no control. And we also show the unfairness, and we observed that essentially we are not fair. So we discussed about different reasons that is causing this problem. I'm not going into detail of that. We don't have time for that. But one source would be different IO intensities, which I think you have some sense of that. Is also very similar to memory intensive and memory non-intensive. For IO also you can have that, IO intensive and IO non-intensive. And we actually showed with some analysis that so we had one fixed flow, flow, or let's say application, that we were reporting the average latency for that application. And there was another flow, which we call it as an interfering flow, like flow that we increase the intensity of the application in terms of megabyte per second. So you can see that by making this interfering application more intensive, the base application is actually experiencing longer latency. So this shows actually how interfering application can cause longer latency for the base application. So that's one of the reasons that we are observing this unfairness. Another reason would be different access patterns, which this also you kind of seen in memory control. We discussed about random memory accesses and streaming access. We discussed about it. So here also we can have that. So there might be some applications that they have kind of we call it here a sequential access pattern in the terminology of storage. So their access pattern is much more sequential. So you can actually distribute them nicely across different queues. But then once you have other applications, so like this, they can actually interfere. So basically that application with very good parallelism cannot benefit from this parallelism. So that can also, essentially this application, this blue application would experience longer, more slowdown, because that red application was generally actually slowed down because there are a lot of requests going to the same queue. But this blue application could actually get very good performance from the parallelism, but now it needs to wait for all this red application to be done. And that can be also another source of problem. Another source would be related to the write and reads, because that's something that we're going to also see much later. In DRAM, the latency of read and write are not that different, but in storage, read and write latency are very much different. Like, so that's why actually people try to usually schedule or prioritize read operations across write operations, because reads are much faster. Like, remember about shortest task first, because read operations are much faster. We want to, probably it's better to schedule them or prioritize them faster. But then that can also run into issue at some point. Another application which is write intensive can cause some, can observe huge slowdown. So that's why we try to we observe that by some experiment that basically it's good to actually prioritize read operations across write, but you should not do it all the time. So there should be also some threshold to understand, okay, how much starvation I'm causing for the write operations. And another source which is related to garbage collection, which I don't have, I don't want to go into it now, but that's also another source which causes interference. Okay, and then essentially we devise our work, Flean, which has a 3-stage I/O request scheduling. It replaces existing transaction scheduling unit inside the storage, and it takes in-flash transactions, reorder them, and sends them to the flash channel. Okay, so in the stage 1, we basically do fairness-aware queue insertion, which mostly in the line of handling the first source of the problem, which is different I/O intensities. So when we have this queue, which we have this, the tail of the queue and the head, and once we have getting requests from the low intensity flows, we try to essentially reorder them. Like this is coming, so we essentially reorder, we put it at the head of this queue. Another stage is priority-aware queue arbitration. So we have different queues, but then so operating system might have different priorities for different applications. So this stage is for that, to make sure that we are obeying the priorities that operating system is, basically, wants to ensure for different applications. And at stage 3, we try to do some weight balancing transaction, essentially mostly related to the read-write ratio and garbage collection, which we try to balance how much latency we are causing for the write operation, because you keep scheduling read operations, but then you make the application with writes with a lot of writes to be stalled. So at some point you need to basically schedule write operation as well. Okay, and then we implement all this, and then we compare with prior work, and we show that here is also very interesting. So one of this prior work is actually the scheduler, which is already implemented prior work in the operating system. So that's a state of the art when you want to do a scheduling at the operating system. So we take that basically a mechanism and we implement it internally inside the storage, and show that Flean actually outperforms that, mainly also because that Flean actually is, now that we are inside the storage, we know much more. So it makes sense to optimize the technique based on our understanding of the storage. Whereas prior OS level techniques, they are kind of not much aware of the storage, and their effectiveness is actually very much limited. And in terms of speed up, also we outperforms prior work. So in the end, Flean is high performance and fair scheduler compared to prior works. And that's more about Flean. If you are interested, you can check it. Question? Okay. This is going to be much more clear when we go into our storage lecture. For example, I couldn't go over the garbage collection part because that needs a lot, at least 1 hour, 30 minutes or 1 hour explanation. So I didn't want to open that now. Okay, so let me conclude if there is no question. Okay, so yeah, in this lecture we discuss, how we can fundamentally, reduce interference and provide, interference control techniques. We discuss different techniques like prioritization, data mapping, core and source throttling, and application thread scheduling. And as you can imagine, base is to combine all, but how would you do that is not easy to do. So there is very much challenging how we combine these techniques. So there is actually very interesting research direction in that line. So approaches in the line of smart versus dumb resources. So smart resources can be, I mean, they are QoS aware, memory scheduling. Dumb resources, basically we need to do source throttling, channel partitioning. Both approaches are effective at reducing interference, but there is no single best approach for all workloads. And that's why we need to combine these different techniques. We discuss also different techniques here, like request thread scheduling, source throttling, and memory partitioning, and then we still also need to combine them for the best result. So if the memory is not aware of quality of service, then we have uncontrollable and unpredictable system, which is very bad. So remember that providing quality of service is one of the key requirements in our system, which is very important for improving performance, predictability, fairness, and utilization of the memory system. And also we discussed many new techniques to minimize memory interference, provide predictable performance, and many new research ideas needed for integrated techniques and closing the interaction with software. However, we did not cover a lot in this line, like prefetch aware shared resource management. Like I had one of your colleague actually pointed very nice thing related. Once we have prefetch requests, then some of our observation may not be correct, which I agree. So it needs to be, but there are also works in that line. I just didn't discuss them. So prefetch aware shared resource management is something that we didn't discuss. DRAM controller co-design, cache interference management, interconnect interference management, write-read scheduling, DRAM designs to reduce interference, and interference and quality of service in processing memory, and many more. So, and the future is going to be bright, I guess. At least we hope. Memory quality of service technique for heterogeneous SoC systems. Like we have many accelerators processing in and near memory, and we need to provide better predictability and higher performance. Combinations of memory and quality of service performance techniques. Like remember about basically our channel partitioning and scheduling technique that we discussed. And potentially, I think I have it here as bold because it's very important to use machine learning techniques to manage resources and as we go more. So remember about this work, self-managed memory controller that we discussed about using reinforcement learning, but that one we only focus on performance essentially, right? So there might be some, these works in the line of, reinforcement learning, for example, to optimize for quality of service, for performance, fairness, and we have not done it. So I expect, my gut feeling would say that, if as you use machine learning techniques, you are much more capable of optimizing. But the question is that how, the complexity, like how simple you can do that is a big question here. So there needs to be research in this line. And hopefully we're going to have real prototypes of, these techniques, which in the end, we should experience, the impact of these researchers in our real life. So hopefully we're going to also see that in future. And with that, that's the end of lecture 11. We are still 7 minutes early. I was expecting that I'm going to be early today. So I wanted to have another lecture today also, but then I just wanted to, to not rush things. So it's good to keep things nice. Tomorrow we're going to have memory robustness, which Professor Mutlu will teach. And next week, we're going to see, what topics we're going to cover. Any question? Yes?
Can you give some example of the DRAM controller? Yes, you mentioned that we didn't discuss.
Yeah. Can you repeat the question? I didn't.
Give some examples in that line.
In which line? I didn't.
DRAM controller,
Oh yeah, DRAM memory control. DRAM controller. We discussed. What do you mean by DRAM controller? Oh, DRAM controller co-design. That's true. What can we exactly? So that needs more changes in the interface. You know that so you have some information of the DRAM, and that information essentially transfer to the memory controller more, and then you. I don't have any you know, some specific works on my top of my head to mention here. It might be my bad, but essentially you by co-designing DRAM chip and also the memory controller together, you might be able to optimize more. You should be able. And so the works that I presented in the line of SMD was through in that direction. You know, once you make the interface from the memory controller and DRAM more transparent, essentially, then you can actually optimize more at the memory controller and also the DRAM. But if you ask about a single example of the work that we have done in this line, yeah, I don't have it at least now on top of my head. Any of you guys remember people from Safari? Any paper in that line? No? Okay. Good question, but I will think about it. I may find something. Any other questions? Okay, great. Then have a nice day, and I think I see you tomorrow. Bye.